Hello, everyone. I'm Anthony Kapkin, editor of Energy Manager Canada, and your host for today's session. I hope you're all ready to learn about low E, high heat, what our building models get wrong about modeling windows. Our presenter is Adrian Edge, Director of Codes and Regulatory Affairs at Fenestration Canada, an industry association representing window and door manufacturers, industry suppliers, and stakeholders serving the Canadian market. Now, without further ado, please welcome Fenestration Canada's Adrian Edge. Adrian, take it away.
Thank you very much, Anthony. And I appreciate Energy Manager Canada giving me another platform to have this conversation. Um, just as a little bit of background before we get into this conversation, before I worked for the association under this role, I managed multifamily development for a window and door manufacturer in Vancouver. So our conversation's going to anchor around a story that I got from that time. And I would love to say that this was a one-off type of situation that builds this conversation, but it wouldn't be much of a conversation if that was the truth. So before we get into that story, let me give you a couple things I'm hoping you'll be able to take away from this conversation. So first is just a basic understanding of how solar heat gain works and how buildings are affected by glass and windows and doors. As a note, I've definitely sculpted this conversation to be around energy advisors, given this is Energy Manager Canada, but I'm hoping there will be something for everyone to take away from the conversation. So once we kind of go through the basics, I've been able to tell you a little bit of the story of how that applies. I'm going to give you some understandings of what happens when it goes wrong and where some of those problems come from. Then we'll get into some of the code changes that are happening at the national level and why they matter, what's going to do as far as the market is concerned. And then again, as an energy advisor, what are some of the things you can be doing? And then as a market overall, some of the things that you could be keeping an eye on. So to start with, I've got this project in Vancouver. It's a passive house project. It has two phases that are separated by about a year. So the first phase has this townhouse complex of about 30 units. A year from now, we're going to wind up doing another 120 units. So this is kind of a unique circumstance where window and door manufacturers, when you're dealing with a multifamily project, you don't typically get involved until you've got a general contractor that has sent out a tender and you're bidding for it. You might get involved a little earlier than that, but not typically much more than that. But in really good energy efficiency projects, I found we were brought in early with the architect and we were able to talk about design, how the windows fit, sizing, configuration of the thing starts to have conversations way early on. So more of like a integrated design process or an IDP. So we get into phase one, and the original design for the project is frankly exactly what you would want from a good energy efficiency project. They have external blinds, good overhangs. They had some solar fin type of solutions. They had a cooling system that was integrated. It was a really well designed envelope. Like the configurations were simple. The red line exercise was really simple for how you apply the envelope. But the one thing that threw me off, because I had dealt with this in the past, was that they were calling out a 0.35 solar heat gain coefficient. So the reason why that threw me off is because it's a bit of a middle ground between what is possible. So especially in a project like this, where the envelope was critical, so we had a triple glazed unit we were going to be using, and that meant that we were either going to have, and I'm going to explain silvers and how low E coatings and solar heat gain works here in a moment, but we had one option that provided us like a 0.26 to a zero point 0.3, and we had another option that provided us kind of a 0.42 to zero point 0.5. So this 0.35, if we had to hit it, frankly just wasn't possible. So let me get into what is a SHGC or a solar heat gain coefficient. So A solar heat gain coefficient is represented is the amount of solar radiation coming through the glass and then being re-radiated as a number between 0 and 1. So 0 being that none of that solar radiation is coming through, and 1 meaning all of the solar radiation is coming through. So a zero point 0.2 would mean 20% of that solar radiation is coming through, and then 80% is being reflected. Zero point 0.6 is 60% of that solar radiation is coming through. So the way that we manage solar heat gain within the window and door world is through the use of silvers, or what we call low-E coatings. So silvers are being applied to the interior surfaces of glass. So for reference, if you've got a two pane piece of glass, you're going to have the exterior surface. So the one that if you're standing outside of your building and you're touching the glass is surface number one. On the interior of that surface, it's surface number two. And then the interior surface, so the piece of glass that you'd be viewing from the inside, is surface number three. And then the portion that you can actually touch would be surface number four. So a silver is typically applied to surface two or surface three. Or in a triple glaze unit, it's two, three, four, five. So these are soft coatings so that if you do touch it, it doesn't smear. There are hard coatings. I'm going to ignore those for this conversation's sake. But for the simplicity of this, if you've got a single layer of silver that's applied, you're going to get the highest amount of solar gain. If you've got two layers of silver or double silver, you're going to get kind of a mid-range of that. But it's actually a pretty substantial jump between single and double. And then between double and triple, you decrease the most amount of solar heat gain. So I had a mentor who actually just recently retired, Al Ugelis, who wrote a paper on thermal comfort with glass. And in his investigations, he was using a program called Hot 2000, which many of the people on this call probably are well acquainted with. And deep in the bowels of that software, there's an interesting concept called relative heat gain. So the benefit of relative heat gain is it takes this solar heat gain coefficient, this percentage of the solar radiation coming through, and it makes it a tangible watts per metered squared. So, in this example, if you were to have a 3 meters cubed or 3 metered squared window, so that's a 6 foot by 5.5 foot window, and you were to have a single silver that's applied to the second surface of the glass, you're going to have roughly about 1,500 watts of energy. So for comparison's sake, that's about a space heater and a half on high inside your house. I should backtrack a little bit and explain that relative heat gain is based off of worst case scenario. So that means at the highest point in the summer on the west face of your building, this is the amount of heat that's going to be coming in. But keep that in mind, if you've got that size window on the west face in the summer, you've got a little space heater inside of your house that you either need to figure out a way to manage that heat, meaning release it from the house, or you need to be able to mechanically cool. Otherwise, you just have heat buildup that isn't being stopped. So this table is being pulled directly from the research paper that Al had put together, that he took a window example and he walked us through, what a single pane of clear glass would look like, double pane air filled, double with a single low-E coating, double with two, three, and a triple with three. And it gives us kind of this spectrum of like what the solar heat gain is in combination to what that relative heat gain it would be inside of your house. So a single pane, clear piece of glass at that 3 meters squared is going to be about 1980 watts of energy, which is going to be two space heaters running on high versus like a triple glazed single low-E coating type of solution is going to be the equivalent of energy to say my MacBook Air is currently using while I give this presentation. So one of the concepts that is kind of challenging to wrap your head around with this is When you get your window, well, when somebody buys a window, the window is going to show up with a label, and the energy label is going to give you that solar heat gain coefficient. But it's important to note that that solar heat gain coefficient is based off of the standard size that that window was modeled to. Admittedly, many of those standard sizes are actually smaller than many of the windows that are going to be produced for people's homes. That as time has gone on, we have seen that the windows continue to increase in size. That's not entirely true. There's a lot of energy efficiency conversations, but I think for general purposes, on average, the standard size is probably going to be smaller than what you experience within your own home. So I'm going to give two examples so you can kind of understand the difference between the amount of energy that is being produced. So if I've got a small casement window, so 24 inches by 60 inches, with a single silver double glazed, it's going to produce about 441 watts of energy. Versus if I take that same configuration and I expand it to like a sliding door, um, that sliding door with the same glazing configuration is going to be 1470 watts of energy. So let's say you went ahead and bought the casement window and you found a manufacturer that could produce a 76 by 76 inch operable window. This is the energy difference that you would be seeing between what you saw on the label and what you're actually going to be experiencing within your home. So I want to go back to the story of the townhouse complex. So we've gone ahead and we've done the design with the architect. We have the project moving along really well. We've got shop drawings that have been completed. We've sent them out for approval. We get the shop drawings back, and we've got a failure from the energy advisor. That the energy advisor has notes that the 0.27 solar heat gain because we're using a two silver low E coating isn't appropriate for the model of the building. Um, to benefit on their side, what they're looking at is if they don't have that 0.35 solar heat gain and they're not incorporating this passive heating solution, their mechanical system has to be sized up. So many of the decisions at this point have been sedimented in such a way that if we were not to meet their model exactly the way they needed it, then they're going to have a serious cost increase. So we get the shop drawings back, and I'm having conversations with the general contractor and the architect, and I realize that the solar fins and the external shading have been removed. The cooling system has been removed from the building. They've left the rough ends for this first round. They still have a really tight envelope, and the energy advisor tells us in conversations that if we can't meet the 0.35, then we want you to go ahead and meet the 0.43 that your single silver is going to create. That's a huge red flag for me, having some of this information in the background, knowing that they have a whole bunch of west-facing solutions that are going to be overheating in the summer. And so I throw a fit, frankly, that we have the general contractor and the architect and the developer all sitting there and we're having conversations. And I explained to them that unfortunately your modeling isn't going to match what the needs are of those inhabitants. You're going to have a passive house building that essentially is going to keep that heat in tight. So being that we're in Vancouver, the way that their permitting system works is that you have to send in your model before the building gets its original go-ahead. And then that model has to align as you actually implement it. So we go to the city of Vancouver, we have a conversation about this issue, and they decide to provide us a variance where they allow a 270 on the west face, but we need to use or a two silver on the west face, and then they allow us a one silver for the rest of the building. So that's their compromise. It wasn't great, but it did help us mitigate some of the worst, call it heat trap type of problems that we were to run into. So I didn't use this word, but I'm just going to throw it out there. The concept of value engineering just irritates me at my core. That it oftentimes I would hear it from people. What it meant was making things cheaper. there is such a thing as value engineering where you are able to tweak things and make them more efficient. But in this kind of case, was really obvious. This was a budget related item, and those items were viewed as optional, which I argue they were not. So we get into phase two. And the exact same process happens. We go through the shop drawing. I get a pushback on the solar heat gain. We try to use the same variation as before, but because the model was already agreed to, it had to go back through another variation through the city of Vancouver. And this time, because it was 120 units, it was too much of a risk to accept the variation. So they were forced into using a single silver for the entirety of that townhouse complex. Um, in addition, value engineered out the rough-ins for the AC units. So not only do you have all the same problems with phase one, but the people that are buying these townhouses also don't have the ability to adapt a mechanical cooling system in to decrease the overheating. Now, I will say right up front, I have not gotten to actually talk to this project after it's been implemented to see how this first summer in the townhouses went. So this is all still very much just looking at the numbers of those houses and getting a feel for it. We did work through some solutions to help them mitigate the heat in the future, but I've now kind of painted the picture of this was happening across many of my projects that we had this 0.35 solar heat gain and the model was telling them they wanted passive heating. So I, the, at the core of the issue for me is that the modeling was showing all the right checkboxes. You know, the U value was right, the energy demand was low, the air tightness was great, the building was really efficient, but it was going to overheat. The internal space was going to get to a place where it was just miserable to live in. So, you know, we got really good at solving one problem, we created a new one. So I will be the first to admit I am not a professional when it comes to Hot 2000, but from the little bit that I've been able to gather, here's some things to keep in mind as you're using Hot 2000. If you see situations where there is a lot of west-facing glazing or a lot of south and west-facing glazing, it's probably good to go ahead and do a individual window model so that you can get an idea of whether or not, you know, the rooms with that west-facing glazing are showing up as 26 degrees or more, especially if they're more than 4 hours in kind of your worst times of the year. There is a proposed code change. So I'll get into this in a moment. There's a slide on how the national code change is changing, but there is a proposed code change that is still in review that if you go over 20 hours of at 26 degrees, then it triggers the requirement for a cooling system. So much of this will actually get into that world. But anyway, so there has actually been a fair bit of research on this subject that, you know, we aren't just coming at this as like a fresh topic and, you know, these are the buildings that I experience. RDH is a engineering outfit in the Lower Mainland. They've actually done a fair bit of expansion since I first started interacting with them. And they have this great research project that they did for BC Housing where they were able to do a survey of many of the buildings in the Lower Mainland. And what they found was that many of the buildings were experiencing over 700 hours above 26 degrees centigrade annually. And the people that were most affected by these buildings were families, young children, seniors, people with health effects. Um, you know, you had kind of one of two situations going on. Either you had buildings that just had a lot of single pane, no low E coating type of glazings that were letting a lot of heat in, and the building just couldn't dissipate that heat fast enough for it to not create these kind of situations. Or they were building really efficient and envelope first type of buildings, and then the even if you had smaller glazing, that heat would build up and then it would create a heat trap. And not to, Vancouver is an interesting problem because it's called a zone four area. So, when we're thinking about climate zones, we're going to have zones between 4 and 8. Zones 4 and 5 are particularly difficult because you've got a lot of sun and you have prolonged heat. But even in some of the colder climates, you still wind up with a lot of sun. Like, so where I currently live, we're in a zone 7A. Many of the homes here are built really efficiently because it's just frankly cold. And so, the sun comes in or that solar radiation comes in and then it has a really hard time dissipating. It's really interesting to me, all the various problems that you can kind of see with this problem as you look across the country, but know that it's a national issue. So from their research, they found that over 500,000 units were affected by this problem. And as climate change as the climate begins to get warmer, this is becoming worse. The cost of retrofitting this solution is pretty considerable. And as I mentioned, there's actually quite a few research projects on this particular topic. Um, so I'm going to give kind of an interesting trigger point that happened in Vancouver, which we had what was called the Vancouver Heat Dome. So we had a series of days that got into like 43 to 48 degrees. It's like 3, 4 days of this, where 619 people died in their homes from overheating. It is one of the worst events in Canada's history when it comes to natural disasters and lives lost. Um, BC's response was to create a an act that would create a 26-degree maximum indoor temperature for no more than 20 hours per year. This is kind of a messy conversation because we were still relying on historical data as the baseline. The temperatures were much lower. So you've got we've actually got an updated code change that's coming that's going to actually make this a bit more realistic. But at the time, we were looking between 1987 and 2016 for those historical models, and they were definitely lower temperatures than what we have been experiencing. Um, so it really did shift the conversation at the, provincial level and then into the national level. So that gets into maybe one of the biggest code changes that are coming down the pipe for the National Building Code. Um, there's two. I mentioned the 2063. The reason I don't include it in this presentation is because I'm not confident that it's actually going to it's going to continue. But for those that have not been involved in code systems, the way that the National Building Code works, you put in, meaning anyone on this call, anyone in Canada could put in a CCR or a change request. That change request goes to task groups at the national level. They review it for applicability to the policy direction of the National Building Code. And then those CCRs are picked as potential PCFs or proposed code changes. This one was put in to create a solar heat gain maximum for windows and doors. So you can kind of see here, it outlines the criteria for, call it zone 4 to zone 8, and the amount of solar heat gain that is an absolute cap. You cannot go above it for these different climate zones based off of the amount of window to wall ratio. So eh, I personally think it was a good path. It's something that will help cap off some of the worst effects. So, this 0.43 that I talked about with a single low E coating, I had projects that was asking me for a zero point 0.7 solar heat gain coefficient, which I'm not quite sure how you get to without having just clear glass, but you had projects that were just asking for this ridiculous passive heating because it was viewed as free energy. So that helps deal with some of those requests and some of the application of those. So the research that kind of sits behind the proposed code change, because each one of these proposed code changes actually have to have an impact analysis and justification for why it would be implemented. is a research article that was put out from the Association of Fenestration in Quebec, the AVFQ. Um, I think it did a really good job of doing an overall survey where it showed that, yes, the higher solar heat gain would reduce energy, but it increased overheating risk. The climate mattered for this, that, in the warmer zones, 4 to 5, which is about 70% of our population, we need a lower solar heat gain. It doesn't make sense to use a higher solar heat gain. And then in climate, like the colder climate zones, 7 and 8, like where I'm living, there is benefit in having that solar heat gain coefficient, but only if it's managed well. That yeah. So they got a little bit into cooling systems versus without cooling systems, which is where the 2063 comes from, that there is uh, there is rationale in using cooling systems. If you're going to have a higher solar heat gain, you need some way to manage it. That's kind of at the end of the day how that plays out. So I, as I mentioned earlier, I think some of these problems can be prevented. And a big portion of that is not allowing the design of these projects to value engineer things out that are critical to the health and safety of its occupants. And frankly, the idea that a project, once the architect, the developer, and the general contractor all agree is a potential problem, but gets usurped by an energy advisor in a city is, I think that probably needs to be checked. There needs to be some discussion about professionals at the table that are able to make the call. If somebody's doing project specific work and they can see that the inhabitants are going to be harmed in safety wise, there needs to be some checks. So if the external shading had been kept on that project that I talked about, where the solar fins have been kept, or the external shading mechanisms had not been removed, you could have stopped some of the heat trap effect. You could have decreased the amount of heat that was coming into the house. If at the very least the rough ends could have been kept for the second phase of the project, you could have included the cooling units, and that could have stopped the heat cycle. Um, and, and this is kind of my big advocate from the window and door world, there is so little cost in the difference between a one silver and a two silver. If you absolutely have to remove these heat management systems, the very least you can do is leave enough silvers that you decrease that, call it heat trap. Because what I honestly think would happen in those kind of situations is that you will wind up with a floor unit in a window that is going to generate more electricity, which completely destroys the whole energy demand conversation. So, as I said, there really is, I think, very little cost in the, call it, proper management of the glass from the get-go. I'm kind of showing this slide as a like after the fact of like you get this wrong, and what you could do is you could replace the glass and you could get an energy divisor to make sure that you've actually like hit your target versus if you have to remedy this with mechanical cooling, it is much more expensive. If you have to add exterior treatments, I've seen a lot of variations on how expensive that can be. So that's its own thing. Is the market probably still needs to develop to add more cost-effective solar fins and external shading devices, but like at least gives you an idea of how much of a cost difference it is between just decreasing this with the low E coating versus having to deal with this after the fact. So for energy advisors, using a size corrected solar heat gain coefficient would make a huge difference. And I've got a little tab at the bottom of this, but Fenestration Canada has actually been working on a size specific calculator that will be published for the public to use. So you'll be able to put in the actual criteria of the windows and then get the appropriate solar heat gain coefficient for the window you're looking at. That'll be a tool that's available. Alternatively, AHA 2000, you do have a little bit of flexibility there. I will admit, I know it's not perfect, but there's still ways to tweak that in and at the very least get to a place that you have um, you've got some idea of the risk that you're taking. Um, at the very least, just check orientation. If you've got a lot of glazing on the west and south faces and you don't have a lot of solar management, somebody's got to raise their hand and just be clear that that's a potential issue. Um, and again, modeling individual windows, I think would make a difference. So, as a recap, the National Building Code is going to have this PCF 1823 that's going to cap the maximum solar heat gain. It may or may not have 2061, not 2063, for the maximum of 20 hours per year. We're currently in what's called a pencils down period with the National Building Code for the 2030 cycle and or the 2025 cycle. We will know at the end of this year whether or not that PCF continued through. And then there was a BC housing policy that did the same. But when it comes to actually talking to customers and the project team, my hope is after this presentation, you can potentially give some ideas to them on, what that heat is and how it affects them. Um, we do have that thermal comfort paper on the Fenestration Canada website. You can use that. Al did a good job of kind of unpacking that formula, so you could apply it. My hope is in the future that the size specific calculator will actually include that relative heat gain measurement so that you can see, how that window is going to impact on the amount of heat gain to the space. Um, Whenever possible, try to prioritize passive strategies first. So this low-E coating is a passive strategy. Solar fins are a passive strategy. Overhangs are a passive strategy. When possible, try to just decrease the amount of solar gain on those areas. Um, and if you can, and I found this was definitely the case whenever we were talking with projects, if you can flag it and document it, oftentimes further down the like further down their portfolio of projects, this shows up and they start questioning it. It does make a difference to have the conversation earlier. That as you document it, you can say like, "Look, we already had this experience. This is how the inhabitants experienced it. It's not necessary. This is the cost that we experienced. We saved. Here's the cost that was implemented after the fact. That almost always, in my experience, you had a higher cost after the fact. So that kind of wraps up my presentation. I really appreciate you guys kind of walking through it with me, and I'm open to questions.
Very good, Adrian. Thank you for that. You brought up a lot of good points, but probably my favorite. Actually, I think I have two favorites. The value engineering. Too often it just means making things cheaper or omitting a bunch of things rather than trying to find ways to achieve the same thing more efficiently. And I love the relative heat gain, the comparison with the space heaters, because that really makes it very easy to understand what is going on internally in that space. So that's fantastic. Before we get to questions, I do want to ask you, um, regarding Fenestration Canada, are there any events coming up where Fenestration Canada is hosting, where people can come see what the association is up to and possibly bump into you, Adrian?
Yeah, so we've got Windoor coming up, and that's our big Window and Door Association get together. It'll be in Toronto this year, October 7th and 7th through the 9th. Normally the 9th is like an event outing type of thing, but the 7th and 8th are our big education days. So yes, come say hi. I'm always happy to meet people from our industry, and I will absolutely be there. Alternatively, we also have chapters throughout the country. So, depending on where you are listening from, there is a chapter for each section of the country. They typically have 3 to 4 live events a year. We also have our AGM, which this upcoming spring, so spring of 2026, we will have it in Quebec City. And then we also have our Fensterbau delegation that's going to Germany in March. So that'll be a fun one where we'll actually have a delegation that goes through and gets to see a lot of what's going on in the international world when it comes to windows and doors.
Very good, very good. So Fenestration Canada is not resting on on its laurels. There's lots of events and lots of opportunities for education, see what's out in the market, and again, possibly bump into you. All right, let's get to some questions. There's one that I think was very slide specific. I don't know if you could bring your slide deck back up, Adrian,
Sure.
but this is probably about, let's see, maybe about, oh, right. There was the slide for cost of getting solar heat gain coefficient wrong. On the left-hand side, you've got the prevention costs, and on the right-hand side, you've got the retrofit cost. Prevention total 2,000,
Yeah. So
retrofit
this guy.
total. Exactly. So one of our attendees asks, are those additional cost estimates for triple silvers compared to single silvers or double silvers?
It's an awesome question. And it's something that I used to. I don't want to speak specifically to each window and door manufacturer because they all will do it a little differently. Sometimes, frankly, it's marketing costs, but the actual cost of getting the difference between like a single silver and a triple silver is pretty negligible. Like you're talking about 1 to 3% of the glass cost. You know, yeah, I'm gonna leave it at that. But I often viewed that difference between 1 to 3 silver cost as something that shouldn't have been much of a nod. As an example, I think I used to have windows, and whenever I was doing the calculation on the variance of cost, it was like the difference of $7 for the glass. It's almost comically limited, and yeah, I'll leave it at that.
So it's almost like you can't afford not to.
I, it's best to choose the glass option that works for your project and for you to know what that need is. Yeah, again, if you're in a colder climate, maybe a higher solar heat gain does make sense. There are practical applications for it. But I would say for the vast majority of projects that I ran into, if you're not willing to do the specific modeling, a two silver solution decreases your risk and is frankly just not worth the call the variance of having overheating in your building. That it is such a common problem to have the overheating that mitigating it at least at this portion of the cycle because it's such a low cost, I always made sense to me.
hmm That that same attendee is also asking about if you can talk about the feedback on the project you referenced. So I'm assuming the townhomes, the phase one and the phase two, from first person, or maybe they're asking if you've had first person occupant accounts, from those occupants. And did a consultant or was a consultant able to go in and take empirical measurements?
Yeah. So you two I made the point, but that for that project, I've not actually gotten any first person accounts for that building. I did have it for other buildings that had similar stories. And yes, we have been through those, or at least when I was at that window and door manufacturer, the consultant did come back and the architect did come back and do some empirical measurements. And yes, it was hot. Like just frankly, it's Vancouver and it was a little more sun and 180 becomes a problem on the west face. So, like, the research is, I think, pretty well seated. I think our math is working. Admittedly, I just don't think the modeling math was working, or the modeling math works for what it's trying to do. The energy efficiency does work the way you think it does until you start having to add another cooling unit when you weren't planning on it.
Well, I do like that you mentioned very near the top that for good energy efficiency projects, that someone like you was brought in early, not at the very end when the tenders are out. Let's get in there with the design and make sure that all those things in the right-hand column that ended up getting scratched out actually stay in there.
Yeah.
Now, tell me, Adrian, uh, how do you see the new solar heat gain coefficient maximums in the National Building Code affecting the way projects approach window and door selection?
I think it kills the outlier projects where they're asking for things that are unreasonable. So, when you've got high energy efficiency projects, which I'm personally, I wish I could put my finger on the crystal ball and say this is the play out of how the country is going to deal with energy efficiency. Like, we've got a roadmap. It's pretty clear that we are heading towards net zero as a country over the next 5 years. That, it is the roadmap. Whether or not it all plays out the way we think it will is a whole separate conversation. But we have our playbook. We're supposed to be getting to net zero. We shouldn't be getting to net zero by making people miserable. So I think at the very least, that national building code item does that. It at a very basic level. And I'm not saying that a zero point 0.5 is acceptable or a 0.45 is acceptable, or frankly, a zero point 0.3 is acceptable. It depends on the project. So, what it does is it gets rid of that zero point 0.6 and zero point 0.7, which frankly shouldn't be possible anyway, because a low E coating is going to decrease the opportunity for solar gain to such a point. But one of the things that gets messy is when we think about NFRC sizes, or sorry, NFRC modeled windows, or CSA 440.2 modeled windows, it is modeled for the entirety of the unit. That's glass and frame, not just center of glass, which is kind of a messy thing when you get into the actual specification world, that there's a mix up. When the window and door manufacturer world gives you a number, it should be a modeled size. It should be frame, outside of glass, and center of glass all together. It's your actual window.
I'm glad you mentioned NFRC in there, uh, because one of the questions I had for you, and you brought it up during your presentation, is Fenestration Canada's size-specific calculator, and then we did have a comment come in. Let me just scroll over here. That NFRC has apparently developed a size-specific performance calculator. Um, how do the two correspond with each other? Does one do one thing? Does the other do another thing? But tell me about Fenestration Canada's first.
Well, because we had actually really good conversations with the NFRC during the development of the process. Actually, let me just quickly outline a short story of how we got here. So the city of Vancouver had their energy modeling guidelines that called out the need for size-specific modeling for windows. So that threw a serious trigger for the window and door world, because we just didn't have the methodology to do so yet. It didn't exist. So over the last 3 or so years, we've been working with the city of Vancouver to develop the language and the methodology necessary to do so. NFRC actually has published the size-specific methodology as part of their standard. So it is, if you are meeting the NFRC standard, you can use this size-specific modeling as part of their methodology space. NFRC has created, I think, one of the things I'd love to see from our tool down the road is a direct relationship back to the NFRC database. So their size-specific modeling will allow a, call it, validation check of the CPD number or the certified product directory, but it is one product at a time. So that is something that is different from ours, which is you can do an entire project on our tool, and you can do it per elevation. I think there's some flexibility on how we play with that modeling in the future. I honestly, I think there's a lot of room for us to continue to partner with NFRC as we have done to kind of make the best out of both tools. But NFRC's tool right now is very much designed as a single point, which I think for many energy advisors could be a good way if you have the NFRC CPD, like you've got a product that used NFRC for its modeling, good way for you to check off that one window on the west face that you're like, hey, that's a risk. I need to go ahead and check that and see how it did, instead of trying to do the entire project. But I think we've made the project tool easy enough to use that it takes 15 minutes, maybe 20 minutes to run an entire project that way. And then you get what the real U value is, what the real solar heat gain coefficient is for the entire project.
Nice. Right. Hopefully that addresses that comment. Another one of our attendees, thanks you for the presentation, Adrian, as do I. Now, I feel like you may have covered this in an earlier slide, but can you share what British Columbia's new maximum indoor temperature is likely to be, or how the new regulations will address this?
It's a great question. I mean, BC already has their maximum indoor temperature at 26 degrees. I don't expect that the temperature is necessarily going to change. I think what will likely happen next is that they'll incorporate more accurate climactic data. So the climactic data from the 2025 code that is going to be implemented, they'll adapt. I say that, and I will not act as the BSSB or the Building Safety Standards branch on this one. They have their own thing. We've had we have a good relationship with them. We talk pretty regularly. And I think there is interest in continuing to improve this particular item. Whether or not they would decrease the temperature or change it, I cannot say. And I frankly would be surprised.
All right. So, jury is still out on that one. But thank you, attendee, for that question. Another one of our guests asks, how do you compare single silver in double glazed versus single silver in triple glazed units in terms of solar heat gain coefficient?
Yeah, great question. So I had that table near the beginning that got pulled from the thermal comfort paper that showed you kind of the difference between single and double glazed without a low E coating. And you could see there was almost like a zero point 0.2, 0.18 difference in the solar heat gain. You can almost think about it in a similar way, where there is, as you're looking at a double glaze unit versus the triple glaze unit, when you add that additional piece of glass, you're also decreasing the amount of solar radiation that's coming through. Um, yeah, so it's kind of tricky as you get further and further down the, call it, percent of thermal heat. It's not like a clean, you lose zero point 0.1 every time you do this thing. It curves, right? So it's going to be doing something similar where you've got a certain percentage loss of it depending on how many panes of glass. And as far as I can tell, there's not a huge difference in the, call it, thickness of glass, at least within, call it, what we consider industry regular. So, 3 millimeters to 6 millimeters is kind of your industry expectation of the thickness of glass that you're going to run into. You can do more, but you really wind up having to source outside of North America to do those kind of things. So
Hmm.
that's kind of your range. And for that range specifically, the solar heat gain doesn't change a ton between that.
Okay, well, this may also address the footnote to that question. How does keeping low E coating on surface 2 or surface 3 in double glazed units affect solar heat gain?
Ah, great question. And it does. And the answer to that conversation is convection and energy dynamics within a unit and how glass bounces energy. It's super interesting and
Ah,
frankly something I am unqualified to give you a proper answer for, other than it does have to do with the convection between your space. So whenever you've got a low E coating on like second surface versus third surface, when you've got light coming in and it bounces off of that area versus you've got it on the third surface and the light can come into the cavity and then have some kind of convection heat and then come back out. It does operate differently. So
okay.
there's some there is some averages that we could probably pull that would give you a percent difference. It's not huge, but it is different, the way that solar heat gain works between those two situations.
Interesting, interesting. Another question. And actually, I do need to thank everyone because the questions are coming fast and furious. One of our attendees asks, so how open are designers or builders, window suppliers to multiple glass options, perhaps two,
Hmm.
based on elevation? They give the example of, for example, solar tuning, high gain package on north and east, and low gain on south and west.
That's an awesome question because I mean, it depends on the manufacturer, and I don't want to answer for all manufacturers, but because, especially in a multifamily building, everything's custom, No issue, in my view. Like many of the, call it core manufacturers I ran into in the multifamily space, absolutely had the ability to put different low E coatings on different surfaces. So if you've got a west elevation, you're trying to decrease the amount of solar radiation on the west face, but you want to, maximize your solar heat gain on the north face, which there's problems with that, not getting into the logistics, but let's just say for conversation's sake, it shouldn't be an issue. That, a lot of times what I would do is on my shop drawings, I, had specific tags for specific windows that would be sent over to our manufacturer, and it really becomes a processing conversation internally. But well within reason, and I would say most manufacturers are used to it, at least in the lower mainland. They were very comfortable using different ones because they were working so hard to try to tune these packages so that they worked for the multifamily buildings.
Interesting. And so I guess the answer to that question is it can be done.
Ask your manufacturer. The one thing is like yes, it increases the risk of windows being put in the wrong spot with the wrong Louis coating, and then that can cause a bit of headache. But yes, it is within reason, and my experience has been that it's something that most manufacturers are willing to do.
Excellent. Another one of our guests asks, and also thanks you for your presentation, Adrian. As a result of the focus on overheating, would heat pumps be seen as a potential tool to address both overheating through the cooling function while also reducing greenhouse gases? Have there been studies or any work done including heat pumps rather than furnaces?
The answer, without me being specific to that space, is yes. I'm aware that there's a lot of work in that space. I wish I could remember the association, and I'm feeling kind of silly that I sit on enough national code items with them that I know that there's a lot out there on the heat pump side. So yes, a great solution is heat pumps. I think a lot of where I see, call it the energy efficiency conversation, rotates around them. Frankly, most of the rebate programs kind of rotate around the heat pump world. So yes, a mechanical cooling system, heat pump type of solution is wonderful. Like that's a great thing. But passive cooling measures are absolutely critical. Like there is no use in putting all of your eggs in a basket of mechanical cooling if you can't first design your building to naturally deal with it. Like the whole benefit that people are thinking about when it comes to high solar heat gain is the passive heating effect. And what's frustrating is that they're right, but they're just right at the wrong time and for the wrong reasons. So it is, yeah, I think there's such a critical nature to thinking about passive measures in a building before you get too invested in the mechanical systems. But the mechanical systems are key to this discussion. We cannot have a conversation about energy efficiency without them. So anyway, I know there's good research out there, and if I could remember the name of that association, I could point you in that direction, but spacing.
Well, and if anyone can remember that, feel free to type it into the Q&A or into the chat and remind the
H
both of us.
HRAI.
Ah, there we go, HRAI. The same guest has a follow-up question in terms of passive measures. Has anyone been looking into the thermal absorption materials integrated into homes to offset solar heat gain, to offset solar heat gain? Is it possibly too expensive yet?
That's an excellent question, and I have no idea. That is outside my realm. I like when I think about, yeah, I don't even know what materials you're talking about is kind of like my first problem. So I apologize. Like I think about insulation and I think about some of the envelope solutions, but an actual heat absorption material, I mean, yeah, anyway, I'd be theorizing if I sat here and I tried to explain what I think on this one. I just don't know enough to give you a clear answer. I apologize.
Very, very Star Trek, but we'll keep our ears open for it. Okay, one last question for you, Adrian. Um, and I might need your help here, just in case there's some acronyms that you would understand that I don't. One of our guests asks or says, I've heard of people rejecting retrofit windows because they are too dark. So two lights off 366 in a triple.
Mm.
Uh, is there any consideration of VT in these discussions?
Yeah, so a couple descriptions so that everybody kind of understands what he means.
Yes, please.
366 is a three silver solution. He's kind of referring specifically to Cardinal's 366 solution. So Cardinal is one of the major IGU manufacturers that Canada gets its IGUs from, or we get our float glass from. There's a couple manufacturers, but Cardinal is one of the main ones. So three silver is what he's talking about.
Okay.
VT is visible light transmittance. So, yes, and the conversation about visible light transmittance is a really interesting one for me. That there is I think, a substantial difference between a two silver solution and a three silver solution. Like when you look at the glass, you can see there's a darkness to the glass that you don't get from the 270. That being said, if I'm balancing, call it a zero point zero 0.02 VT number, meaning that I'm getting I can't even remember at the moment what the measurements are around VT. I had to spend a lot of time down this rabbit hole because it is one of the big things that shows up with architects is that they get kind of bent on, I really want as much visible light transmittance as possible. And there are calculators on, call it health impact, when it comes to the amount of visible light that you're getting. So we could be having a conversation about health when it comes to visible light transmittance versus health when it comes to solar heat gain. I am going to, without clear documentation, which is very risky in my world, say that the risk to someone's health from overheating exceeds by a couple factors the risk of people not getting the limited amount of visible light transmittant difference between these two versions of low E coating. So I don't want to diminish the value in getting more light through. I think that's really important, and I would love to see a bigger conversation about how do we change some of our materials so we can get both and. But at this time, because we don't have a lot of those, call it market transformation type of needs being met, the balance has to be towards decreasing the amount of heat gain inside of the building if you do not already have the other features to decrease it.
I think that's a fair statement. If you had to pick one or the other, that overheating does sound a little more dire than maybe not having as bright a room as you would like. So I,
Yeah.
I thank you for that. And Adrian, on behalf of Energy Manager Canada, I thank you for coming on to discuss these projects, these changes, these nuances, really ultimately with the goal that ideally we're all talking to each other. We're not just looking at numbers on an Excel sheet or on our clipboard, but we're actually getting feedback from people in the know, all the project participants. So thank you for that. And to our audience, great questions. We didn't manage to get to all of them. We tried to get to most of them, but thanks for being active and participating in low E high heat. Again, Adrian, thank you. Our guests, our audience, thank you for coming on. And that's a wrap. Thank you for joining us today.